Alright, so an extension of what we worked on with disks and washers. With disks and washers we had a circle, and so that gave us pi r squared for the area, pi r squared, and then we factored out the pi. But what we had was the cross-sectional area of those circles, pi r squared. The height was given to us by the integral. So here, now, we're going to have different shapes, possibly not circles. So we'll start off. So what they're going to do is they're going to tell you what the bottom is, the base, what shape it is. It's usually defined by a curve or equation. And so that equation you have to kind of figure out, well, so they'll tell you what shape it is. So a square, for example, we have a squared, so it's saying the base is that and the cross sections are squares. So the distance from here to the function, or f of x, that is going to be this side of the square. And then a square has equal sides, so this will also be f of x. So the cross-sectional area of that is going to be the function squared. The function gives us this value, f of x, and if it's a square, this will also be f of x. So we'll get f of x squared for the cross-sectional area, and then we'll integrate across those values to get the rest of the volume. Now, another thing that we can have is a right isosceles triangle. So a right isosceles triangle, if you think about it, is half of a square. So that would be the same thing times 1/2 if it was a right isosceles triangle. So I'm trying to go over some of the most common ones that you'll see. Now, if it's a semicircle, you have to be careful. So a semicircle is going to be 1/2 pi r squared. Right? A semicircle is half a circle. The area of a circle is pi r squared. So it's going to be 1/2 pi r squared, or pi over 2. Now, what you have to determine is, so here, if we look at this one, that circle, the radius is right here. So in that case, the radius itself would actually be 1/2 of the function, because the function is actually the diameter in this example. Now there are times when they will put the radius across there and they'll have you draw a semicircle all the way over here to the other side. And in that case, then the function is the radius if you're going all the way over here to the other side. But in this example here, the radius is only half of the value of the function. So you need to pay attention to what the radius is. Okay. Now in this next one, what we have is an equilateral triangle. And so here's the formula for it, but I just want to go over how we get that. So in an equilateral triangle, all these angles are going to be 60, and then both of these will be 30. So that's going to be a 30, 60, 90 triangle. So if the base is the function, then this is going to be half of that. And that's the short leg of the triangle. So to get from the short leg to the long leg, we multiply by √3. So that's going to be √3 over 2 in this case, if we multiply this by √3. And so we'll have that. And then if we take the area of the equilateral triangle, it would be 1/2 the base times the height. Well, the base is f of x, and the height is √3 over 2 f of x. So if we multiply those together, we get √3 over 4, and we get f of x squared. So in all of these cases, we have the function squared. We may have to modify the function for a semicircle. So these are just some, if we have them memorized, it kind of helps us out to be able to do the problem. Okay, so technically this kind of goes with the lesson before on disks and washers, so I just continued the examples here, but we also could have started them over as example 1, 2, 3, but it's the same section of the book, 6.2. Okay, 6.2. All right. So let's try it out and see what we get here. So the base is bounded by a circle, x squared plus y squared equals 4. So if we square root that, we're going to get 2. So 2 in each direction, like so. Okay. Alright, so they told us it was a circle, but we should have known that without them saying that. The center is 0, 0, the radius is 2, so let's try to graph that. Usually the mistake people make when they try and draw a circle is they smush the sides down, so I try to keep it rounded out there. Not that it's a big deal, but okay, so let's see. The cross sections are squares. It says find the volume, so pretty much immediately we should have had an integral. And we're going across there, so, well actually let's look at this. So perpendicular to the x-axis. The x-axis is y equals 0, and so it's the opposite of that, so it's going to be dx. So we're going across there, so that's minus 2 to 2. Not sure how much space I need here. Opposite, so this is going to be dx. Now, if you think about it, the square is going to go all the way across here. So that's the length of the side of the square. Now, you've got to imagine the square is going to come up, and there are going to be squares across there as well. So as we go across here, the squares are going to get smaller. Alright, so I actually have a demonstration of this. So here is a circle graphed on there. The scale here is hard to see. Those are 1/2, so that says 2. So it actually matches our radius of 2, so that's our circle. So I'm going to drop this back to give it more of a three-dimensional feel. So we've moved the x-axis, the y-axis down to the ground sort of, so that this is laying on the ground. We're looking at it from the side. Okay, so those represent the sides of the squares that we're going to go across. We'll just put 4 squares on there right now. So obviously a square closer to the edge will be smaller, and then the square at the diameter will be the largest square. Okay, so if we take a square and we move across, so that's showing you how the squares get bigger and bigger until you get to the diameter, and then the squares get smaller or smaller when they come back down the other side. So here's the three-dimensional shape that we should get. This is what it would kind of look like. So it's curved both across the top and curved around the sides also. It's getting kind of slow there, but wait for that to come down. And it's going to kind of shoot through and start over again. So then I'm just going to switch to, there it is. Okay, and we can slide a square inside of it to show. So that's the skeleton kind of the shell of it, and then that's the squares going across to show you what they look like. Okay, so I don't want to spend too much time on this, but we can do it with we put a triangle on the bottom, so now our base is this triangle, and we can go like that. So here they're semicircles with a triangular base, so that kind of makes that half cone there to the side. So that's just showing you a couple of different situations here. I don't really like that one that much, so I'm going to close out of that, I think. So we need to think about this length here. So if we take this equation and we have y squared equals 4 minus x squared, and we square root that, then we're going to get the absolute value of y equals the square root of 4 minus x squared, and then y will be the positive of that and the negative of that. So the positive branch will be up here. That would be 4 minus x squared, and this one would be negative square root of 4 minus x squared. Okay? So if you think about this length here, you can take the top minus the bottom. If you take this minus this, that would give us 2 of those. Or you can just double that, either way. So now, if we come back here, we're going to have 2 times the square root of 4 minus x squared squared. Okay? Now, if we think about that, this is symmetric. So if we apply symmetry to this, we can multiply by 2, and we can just go from 0 to 2 instead. Now I'm also going to square this, so that would be 4, and squaring that, that's going to be 4 minus x squared. It's just going to cancel out the square root, basically. Inverse operations there. So now we have this. We can factor this 4 out and put it with the 2, so that would be 8. And then inside here, we would have 4x, and then add 1 to the exponent, divide by the new exponent, and that's from 0 to 2. So if we plug 2 in there, we're going to get 8 minus 8/3 minus, and then technically we should have parentheses there, but it's going to be 0, so it's not a big deal. Okay, so now if we multiply this by 3 over 3, we would get 24 over 3, and if we subtract that, we would get 16 over 3. So that's 80 plus 48, that's 128 over 3 for the volume. Alright, so if you have any questions on that, please come to office hours. Okay, so let's try another one. So now the base of a solid is so from the very beginning it says that that's going to be a volume. So we're going to be integrating. And the base of the solid is the region between the x-axis and this. So this is a parabola shifted reflected over the x-axis and shifted up 4. So probably can graph that fairly quickly. Like this. Like this. Okay. Now, the vertical cross sections of the solid perpendicular to the y-axis are semicircles. So, perpendicular to the y-axis is x equals 0, and the opposite of that is going to be dy. So that's going to be a little bit more challenging, maybe. So we need to think about this way. So we're going to get semicircles across here. Now, I don't want to try and draw a semicircle across there because it's going to look a little awkward. But the key here is that the radius is actually going to be the y, the function in terms of y, because it's going all the way across there. So we don't have to take half of it like I showed in the picture up here, where it would have been, the radius would have been half of that distance. Because we're going all the way across here, the radius is just going to be that distance. So, couple things. We need to solve this for y. So if we add the x squared to the other side and subtract y, and then square root, we would get that. So that's our radius. That is the distance from here to here in terms of y. So we have a semicircle, so that's going to be pi over 2, 1/2 pi. And then the radius of that is this function over here, so we're going to have the square root of 4 minus y squared dy, because it's the opposite of this. And then what are we going from? We're going from here, we're going on y. So y equals 0 to y equals 4. Okay, it also said the x-axis, so that was our other boundary here. So we were our base is across here, and then we have semicircles across there. So we're going from 0 to 4 on y. Okay, so setting it up is the main thing. Sometimes that's all they ask you for on the AP test. So if we square the square root, we just get 4 minus y, so that's nice. Now if we integrate that, it's going to be 4y minus 1/2 y squared, add 1 to the exponent, divide by the new exponent, and that's going from 0 to 4. So we have pi over 2, and we have plug in 4, so we're going to have 16, plug in 4, 16, half 16 is 8, so that's minus 8, minus, plug in 0, you're going to get 0 minus 0. I just want to be careful because it's not always 0, so I want to emphasize to put parentheses around that second group there. So that's 8. 8 times pi over 2 is 4 pi. So the volume would be 4 pi. Okay. We normally don't worry about units unless they specifically say something about that. So let's try another one. So the base of the solid, so again, the question was talking about an volume. The directions for all of these were volumes. So I have an integral because I saw the word volume. And then equilateral triangles, so that's root 3 over 4 from the formula up there. And so the next thing I kind of want to do, perpendicular to the x-axis. The x-axis is y equals 0, so this is going to be dx. Okay, and then this is going to be whatever squared. And so kind of the only two things we need to find out is what do we need to put in here and what are we going from. Okay, so this is a line with a y-intercept of 1. I think I will call this 1. We'll go by halves. And I'll call this 1 and 2. Hopefully that'll work. And this is going to be negative 1. Okay, so the y-intercept is 1 and the slope is negative 1/2. So that is done. And now the other one, I don't know if you saw me do that, but the other one has a y-intercept of negative 1 and it has a positive 1/2 slope. So that is going to be right here. Okay. Alright, so our equilateral triangles are coming across here. So this is the ground, and we have equilateral triangles coming up all the way across there. So to find that length, remember it's top minus the bottom. That's going to give us that distance there. So the top was 1 minus x over 2 minus the bottom, which was negative 1 plus x over 2. Okay, so if we do this, that's plus 1, so that's going to be 2, and that's going to be minus this minus this. So that's going to be minus 2x over 2, which is just minus x. So that is 2 minus x. So if we square that, multiply those together and double it, and square that, we get that. And then if we integrate, that's going to be 4x, add 1 to the exponent, divide by the new exponent, and 1/3 x cubed, 0, oh, I never put the numbers here, so 0 to 2, 0 to 2. And we're going to get those off the graph usually. Okay, so root 3 over 4, plug in 2, that's going to be 8, plug in 2, that's going to be minus 8, plug in 2, 2 cubed is 8, that's 8/3, minus and 0, 0, 0, so I'm not going to write 3 zeros out there. These are going to cancel, so we have this times this, 8 over 4 is 2, so 2 root 3 over 3. Alright, that's good stuff there. Okay, let's look at this last page. We just have one more page. Just a 2-page notes today. So remember that number 1 and number 2 are calculator questions, but that doesn't mean you're going to be needing the calculator on every step. Same thing for the multiple choice. Just because I would say, I don't even know, half the multiple choice calculator questions, the calculators of no help whatsoever. Why do they do that? I don't really know. Okay, so this was the 2017 test. It says you have a tank, has a height of 10 feet. Based on the following model, find the volume of the tank. Okay, so as soon as you see that volume, most likely we're talking about an integral. Okay, and so indicate units of measure. So you want to be careful about that. Anytime they say that, you need to make sure that you have the units of measure on there. So let's see. Based on the volume model, find the volume of the tank. They indicate the area in square feet of the horizontal cross section at height h feet is modeled by the function f given by this. Okay, so the horizontal, so going across, so the height is 10. So the going across, the cross-sectional area is given by this. So we're going from 0 to 10. Horizontal height 10 feet, so 0 to 10. And then remember, what goes in here? The cross-sectional area. Now also, remember when we do these questions, we can just write the function that they give us. So I don't need to write all that out. I might make a mistake and put the decimal in the wrong place or put a minus and mess that up. So just use the name. Okay? Use the name of the function in here. Okay? And now, one mistake that students make on that is a lot of students want to square that because all the formulas had squared. But that was because we had to square them to get the cross-sectional area. Like if we have a square, the function was representing one side of the square, so we had to multiply f of whatever f of x times f of x. So that's why we squared it. This is already the cross-sectional area. They're already giving us that area. So we do not square it. Alright, and so then you would just type this in your calculator. If you don't know how to do that, you need to ask me in office hours. And so that's just going to be 101.325. You absolutely have to round it off to the proper decimal. And then don't forget the units. So the height was in feet, so the volume is going to be in feet cubed. There was no other units involved in there, so that would be it. Okay? Now, as far as points go, they gave a point for this and a point for this answer. And then, that was part C of the question, and there's a part D as well. So they also gave a point for the units, but you had to have the units right on both of them. So that and down here. Okay? Alright, so if you have questions on that, make sure you come back and let me know. So now, what about this question? Water is pumped into the tank. When the height of the water is 8 feet, okay, the height is increasing at a rate of, so right there you should be all over that. You should be like, okay, the height is increasing. So that's dH dt. So dH dt is 0.26 feet per minute. So you take notes on the question while you're reading the question. Using the model from part C, okay, find the rate at which the volume of the water, okay, so now find the rate of the volume. So that is dV dt. That's what we're trying to find. Okay. We also have this height being 5 feet up there. We don't forget about that. With respect to time, when the height of the water is 5 feet, indicate units of measure. Okay, so let's think about this for a second. We had the volume in terms of h was equal to the integral from 0 to h of f of x dx. Now, you want to be careful here. You want to make sure that these are different variables. That matters. Because we're about to take the derivative of both sides. So that was for volume. We want to find dV dt, so we need to take the derivative of both sides with respect to time. So that means this is going to be dV dt. And here, when you take the derivative of an integral, you just plug it in. So that's going to be f of h. But you don't just plug it in. you also have to multiply by, right, the chain rule. You have to apply the chain rule. So we're going to have to multiply that by dh dt. That's the derivative of that. Okay? So, and then we were told to evaluate that at 5. So this is going to be f of 5, which we can just, and that's why you're supposed to type this into these functions. You're supposed to type them in your calculator. So you should type that into y1 and leave it there, because later on we're going to use it again down here. And if we already have it in y1, that saves us time. Now, dh dt, they already gave us. That was 0.26. So we're going to multiply by that. And and how you can do that for this on your calculator is, if you have that in y1, like I said, y1 of 5, you can just use that actually, and you can just multiply that by 0.26, and then that's going to be 1.694. Again, make sure you're accurate to this. Now it's the change of the volume. Volume would be measured in feet cubed, and it's still going to be per minute. Okay, and so points off of that, actually they gave a point for mentioning f of h, and for having dh dt in your work, and for this decimal right here. So that's okay, probably tricky overall, but and then again, this point, you have to have both of these units right up here. Alright, it's about that time. Have a good day.